It is not AI, just eccentric drilling. But firstly, let's run it back so I can explain the whole repair. This part right here is a track tensioner for an excavator. If you're not sure what that is, the name says it all. It basically just tensions the track. Anyways, this excavator needs a lot of work on its undercarriage. But today I'm going to show you how I repaired the tensioners. I don't have the machinery with me to do this repair on site, so I'm loading them up and taking them to the workshop. The issue with the tensioners is that they cannot hold their positions once the excavator's tracks have been tensioned correctly. And the reason for this is the tensioner's damaged shafts. Let me explain. Grease gets pumped through a grease fitting on the shaft. The grease then travels through the shaft and into a chamber behind the shaft, which is also known as the barrel. Once the volume of the barrel has been filled with grease, and you continue to pump the grease in, it creates pressure. This pressure pushes the shaft outwards, and as the shaft moves outwards, it would tension the excavator's tracks. But because the outer surface of these shafts are damaged, the tensioner's seals are not sealing on them properly. This results in the excavator's tracks to keep slacking and not hold the tension. The damaged shafts also damaged the seals, so I'll be replacing those as well. Each tensioner only has two seals, a pressure seal and a wiper seal. Alright, I got the two shafts out, so I took measurements and made a sketch. I've got my new material, so I can head to the lathe. Let's just have a quick look at the old pin. This hole is where the grease exits the shaft and enters the barrel, and this threaded hole is where the grease fitting is inserted. There are two other holes that house pins. Here's one of the pins I removed with a sliding hammer. The purpose of the two small pins is to prevent the tensioner shaft from rotating. Alright, let's machine the new pins. The material for the pins is induction hardened chrome shaft. This material has an extremely hard, wear-resistant outer layer. I use this material for most machine pins and hydraulic cylinder rods. And that's all the lathe work on this side of the pin, so I'm going to give it a flip. This side of the pin sparked a lot of debate in the comments on the previous video. I'm going to soon be doing some eccentric drilling for the grease passage on the pin. I recently posted a short video of the eccentric drilling, and many people in the comments were arguing that it was AI. I think this was confusing people because the pin was rotating off-center when I was drilling the hole. Many people watching the videos don't work on lathes, so I thought I'll explain to you. The grease hole is not located center on the shaft. So I have punched the shaft where the center of the grease hole needs to be. I then clamped the shaft off-center in a 4-jaw chuck, so the punch mark does not hop when the shaft rotates. And that's basically all it is. It just seems to be like an optical illusion because the shaft is rotating off its center axis. I hope that makes sense to you, so let's begin the eccentric drilling. It really does look unusual. And in case you're wondering, drilling an eccentric hole or a normal hole has no different impact on the drill bit itself. For me, the only thing I was a little bit nervous for was this long drill bit I had to use. With the small diameter long drill bit, you have to continuously remove the shavings. If the shavings clog up too much in the hole, it can result in the drill bit snapping. This would be a disaster for me, as I only have this one long drill bit. And if this drill bit gets stuck in such a deep hole, it will be a mission to get it out. So I had no room for error. Anyways, I played it safe. I drilled about 10 mils at a time, removed the drill bit and cleaned out the shavings. And that's all the lathe work needed for the pins. Next up, it was time to drill some holes in the milling machine. You can use a dividing head for this, it is a lot easier, but the dividing head I have has a small chuck and cannot hold this pin. And besides, this way is good enough for this job, it does not have to be very precise. The reason I'm heating the pin before drilling it is because the induction hardened chrome layer is extremely hard and a normal drill bit will not drill through it. Next up, I'm going to tap the hole for the grease fitting. The grease fitting seals on this taper face, so I'm going to spray some marking glue on it, fasten it and make sure it is seated all the way around. As you can see, there's a line all the way around with the marking glue scraped off. This means it was seated properly. I can now rotate the pin to drill the 2 holes for the stoppers. As mentioned before, these 2 small pins would just fit into the holes with a tight fit. I'm changing the design a bit. I want my pins to screw in on a thread. And that was the first hole complete. I now need to rotate the pin 180 degrees and do the second hole. And that's all the drilling for the pin complete. I just need to tap the last hole and I'm done by the milling machine. To finish off the pin, I quickly went back to the lathe to polish out the heat marks. And that's that for the pins. Let's assemble everything. I only showed you how I machined one pin, but I repeated the process for the second one. I mentioned my locking pins were going to screw in. I used Allen cap bolts for this. I just want to better explain their purpose. The stoppers locate into 2 grooves. This prevents the shaft from rotating, so the grease fitting is always in the same position. I quickly cut the bolts into the correct lengths, and this is how the pins look complete. I now need to fit the new seals and slide the shafts in. I used red rubber grease to help me insert the shafts. And everything came together perfectly. But my job is not yet done. The tensioners need a quick spray paint, then I have to head back to site and fit them. And I'm back on site to fit the repaired tensioners. Before I tested the tensioners, I had a lot of other work on the excavator, but let's skip through that for the video. Here you can see the grease gun connected to the grease fitting on the shaft. This is why the shaft needs the stoppers. If the shaft rotates, you'll not be able to get your grease gun connected to the fitting. The tensioners were pumped with grease until the tracks had the correct slack. And the tensioners are working perfectly. They are no longer losing grease and the tracks are not slacking. Thanks for watching, guys. See you in the next one. Cheers.